Thank you very much, Anders. So yes, today I'll be talking about setoids and their connections to several notions of categories. And for those joining on the recording, this was the picture that we just had a bit of discussion about of Erik at the Mittag Leffler, trying to place also which other people we could recognize from behind in the audience. And I think the consensus was this was probably the semester on constructive mathematics in 2001. But yes, so the everything I'll be talking about today is pretty much sort of rumination on setoids, and I'll say a bit more in a moment where the rumination's coming from. But for those not kind of up to speed, what is a setoid? Setoids come from, I'm sure the idea goes back further, but the locus classicus for it in constructive maths is Erik Bishop's work, which there are several good quotes summing it up. The idea that in a constructive practice, a set should be defined very concretely by saying, firstly, what its elements are, how you construct elements, and then on the other hand, what the equality of elements is, what must be done in order to show that two elements are equal. And this isn't different from what you do in classical maths. I mean, in classical maths, this is a pretty accurate description of how you define sets. Very often in classical maths, many important sets are defined by first saying, all right, the real numbers are Cauchy sequences of rationals, and then they're equal if they converge to the same thing. But when we say that in a classical mathematical context, what we mean is, here is a set in an equivalence relation, and then we take the quotient. And then the big difference in constructive maths is that you don't take the quotient. Instead, this having some kind of underlying thing of elements, and then an explicit equivalence relation on these, this is what you take as the definition of a set, or to avoid ambiguity in the terminology, it's, so some works call it set, but I will follow the tradition of calling it a setoid to be very clear that it's so close to what a constructive mathematician would mean, classical mathematician means by a set. It has an explicitly given equivalence relation. And this has been a very important part of the basis of development in several of the flavors of constructive mathematics, and certainly Bishop-style constructive mathematics and lots of the type theoretic development. So setting it up, being a little precise for a moment about what we mean by it, I'll work for the whole of today in a type theoretic setting, and I'll totally ignore size or universe issues. By a setoid, I mean a type X together with some type-valued binary relation on it, which we write always with the twiddles, which should satisfy reflexivity, symmetry, and transitivity. So it's an equivalence relation. Being a little extra pedantic for a moment, when I say satisfying these things, I mean that, again, it's further data. It's equipped with functions witnessing these things. I won't belabor that kind of language through the rest of the talk, but I want to say it once for the sake of being absolutely clear about it. And similarly, a setoid map is when we have a map of setoids, we need, on the one hand, a function on the underlying types, and then we need it to preserve the equality. And so in the developments of constructive mathematics that are based on setoids, what one does is that one bases most or all mathematical structures, your algebraic structures, your other sorts of things, not on bare sets or types, but on setoids with the equivalence relations. And then similarly, when you've got an algebraic structure, your ring or whatever, all the operations of the algebraic structure will be setoid maps, will be extensional, here's one term for it, they will preserve the setoid equality relation. And the advantages of this, and the reasons why we do it, are that it gives clearer constructive content than taking quotients. On the one hand, because often constructions that you're giving, mappings from one type of structure to another, they're given constructively by some kind of clear computational action on representatives. If one has quotiented the representatives, then that clear constructive action may be lost. For instance, that the fallback from trichotomy that's available in the real numbers constructively is that for any number, it's either, let's say, less than 1 or greater than 0. You can determine something like that. And if you're given a representative, you can determine one of those two options. If you've quotiented, then you can't prove necessarily that you can determine one of those two options. But on representatives, you have a function which takes any Cauchy sequence of rationals, any suitably defined, to either the sort of the tag it's less than 1 such that it is, or the tag that it's greater than 0. You can pick which one of those cases holds. And on the other hand, the other advantage of setoids is that you have less foundational commitment than if you want to work with sets and take quotients. That again, for a start, if you want to work with sets and take quotients of things, you need to have quotients in your foundational system. So that's one extra commitment, but also you're more likely to need some classicality, some axiom of choice to do to prove some of the things you want than if you stick with the setoids and the representatives. On the other hand, there are costs to it. There are disadvantages. I'm reluctant to say disadvantages because I like setoids, but costs certainly, which is the biggest one that's what kind of widely known by people who've done this at all are, there's a lot of bureaucracy and boilerplate lemmas that have to be proven, which I'll go into more concretely in a minute. And also there are some, in some places, not in others, but in some, there are some quite subtle pitfalls and mistakes one can easily fall into giving definitions the wrong way. And again, I'll look at those in a minute. And then the third is a more sort of philosophical objection, but I think it's a quite widely felt one, which is that in some way they're a little bit alien to the spirit of mathematics. And they're maybe a kind of a hack for the sake of being a bit more constructive, but that they're not really conceptually so much part of what we'd like to be looking at the mathematical world as. So, all right, so there's these advantages to them and the costs. And the costs are respectively, especially the sides of the sort of bureaucracy and then the subtle pitfalls one can fall into a bit, are often known as setoid hell. And then what we'll be talking about today, what we'll be going over today, is sort of the kind of the upshot of the perspective on setoids that I got in my first few years coming to Stockholm, coming especially out of a lot of conversations and formalization work with Erik and others in the group here at the time, which gave me a bit of a new perspective on setoids from what I'd picked up as the kind of common wisdom about them before coming to Stockholm. I think Sweden in general has always had a bit of a special culture of setoids, not just Sweden, but Sweden has quite a strong culture of setoids. And Erik had a nice phrasing that he had several kind of titles and slogans that played on, which was that instead of saying setoid hell, we should say something like bishop's purgatory and see it as kind of a step on the path to Cantor's paradise. So what is, when I'm saying all this about setoid hell, what kind of, I mean, those of you who have formalized or carefully worked out anything sort of significantly non-trivial with setoids will already know what I mean, even if you haven't heard the term before. Those who haven't, what kind of things do we mean? The most obvious part is simply that you're always carrying around slightly more complicated objects than when you're just working with sets. A setoid it's got extra data compared to a set. You need to say explicitly what all your constructions do on it when you take a function setoid or whatever else, whereas with sets, you just take the functions. With the setoid equality, you have to give the new equivalence relation on the function space. You have to prove your function's respect equality and so on. But it gets even worse when you have dependently sorted structures that you're trying to work with. So for instance, if we're having a dependently sorted structure built out of setoids, a question we have to ask first is, what is a family of setoids indexed over a setoid? Well, that doesn't sound so bad. So you go in and you try to write it down and you've got a setoid X. What's a family of setoids Y indexed over X? Well, okay, so for each point in the base setoid, we'll have some type of elements over it. And then let's see, and then we want some setoid relations on Y. Where should they be? Probably, first thing you might think of is that they're on each of those types over each element of the base. Or maybe, hang on, but also, if we've got two equal elements of the base, then things in the fibers over them, we should also think of in some sense as living in the same member of the family. So maybe we should have the binary relation should go between those. And also we've got to respect the equivalence in the base somehow, maybe. If we have things in two different, if we have x is equivalent to x primed in the base, and then we have something that in y living over x, should we be able to get something in y living over x primed? Probably. And how should that play with the symmetry and reflexivity and transitivity and so on x? And I won't give the definition now because there's no one right answer. There's several correct definitions, or several definitions one can give which can all be correct. And which are equivalent to each other in suitable ways. There are also some definitions you might reasonably write down and think were correct, and you might convince readers they are correct for a bit, but which turn out to be not quite correct. There are also some quite interestingly subtle pitfalls with using the correct definitions, in that, say, if you write down 2 or 3 of the correct definitions, they're similar enough that then the constructions you do to work with them, you could write down the construction from one definition and use it with the other definition, and it would look plausible for a minute, but it turns out to give the wrong thing because if you've got a slight mismatch. And these mistakes, I mean, they're very easy to make, they're reasonable, and they have been made. So it's really more subtle than you might think going in to do this right. And so to cope with this, we need a kind of good organizing framework to keep us on the right tracks working with setoids. And one powerful organizational framework for this is viewing setoids as a translation between type theories, that you can see it as going from a quite extensional type theory of some sorts, so in particular one with quotients, into a more intentional kind of type theory, which is the more minimal foundational commitment sort of place where you would want to work explicitly with setoids. And so a type of the more extensional theory can get translated into a setoid in the more intentional theory. I'm very deliberately leaving it open what type theories these are. There are a lot of different type theories one could put on either side of this transformation, but the general idea is from a more extensional kind of place to a more intentional one. And this has been developed by various authors. I realized when I was preparing these slides and then didn't get around to checking it properly because of all the organizational things that were going on at the last minute. I don't actually know off the top of my head who first did give this translation. But it's been developed by quite a few authors. And one of the lines of work that has developed it most deeply, and I think very interestingly, is Maeti and Sambin's Minimalist Foundation, which takes this as a very fundamental part of the picture it provides. And then the nice thing here is that lots of the boilerplate lemmas that you need and so on, they're automatically provided by the translation. And it's perhaps worth comparing some other foundational translations we have around, the double negation translation, the true construction from linear logic to intuitionist to higher order logic that Schulman observed a few years ago kind of gives rise to several of the ways that things like partners relations and so on are used in a lot of constructive mathematics. And then one of a very different flavor is program extraction and realizability. So all of these are slightly different flavors and get used and studied in slightly different ways. And so I'm listing them here not exactly for the sake of the parallels as much as for the sake of the differences, but also maybe to suggest that we could have more parallel in how we view these than we do. A different kind of useful organizational framework is category theory. And there is a notion of a kind of category used which works very well with setoids. It's built out of setoids and it's very appropriate for organizing setoids and setoid-based structures. And this is an E category, which as far as I know, was introduced by Erik, but I'm not certain. Please do correct me if I'm wrong. So an E category has a type of object, not a setoid of objects. No, not a setoid of objects, just a type of objects. And then the setoids are morphisms between each two objects, homosetoids, and then identity composition maps, which are all setoid maps. They preserve the equality, and it all satisfies the category axioms up to the setoid equality. And the idea is that the fact that it's a type of object, not a setoid, reflects how in category theoretic practice, one doesn't think of objects of a category as having a strict kind of equality. And the original motivation for this was organizing setoid-based algebra in the same way that classical categories organize set-based algebra. But it also then helps, for instance, sort out the families of setoids problem, or provide one quite good clear answer to it, which is, given a setoid, you can look at it as a discrete E category, just like looking at a set as a discrete category. Look at a setoid as a discrete E category, where the elements of the setoid become the objects of the category, and the equality of the setoid becomes the homsets, the arrows of the category, and then the equality between the arrows is trivial. Any two arrows are equal. And now we can straightforwardly define a family of setoids is just a functor from the discrete category on it into the category of setoids. And so this it leads us, using the categories this way, points us to a quite clean definition that sets up what the families of setoids are and how we should use some of the constructions on them. So E categories are very useful as an organizing principle and a framework in a lot of ways, but they're outside of the image of the translation, the setoids seen as a translation, since the objects aren't a setoid. And so if one's wanting to use these, then one has to move to the point of view that the translation can be kind of guiding, but isn't the whole of how we're using setoids. And then this is maybe more analogous to the way that we use the double negation translation or the true translation of linear logic, that when we're doing constructive maths, we very often have in mind the double negation translation of classical logic, and we use things that can be inspired or guided by it all the time. But at the same time, it's not at all the kind of everything we do. A lot of what we do, is outside that translation. But it's a very valuable translation to have. It's guiding, and it tells us how we can do certain things, how they're going to behave. And provides certain kinds of boilerplate lemmas and so on automatically. One thing that, so this is a shift for a bit, but we'll rejoin the previous path in a moment. One thing that the E categories may have reminded you of, if you are kind of a bit of a hot univalent foundation sort of person, is the definition, the development of categories in hot, given in the hot book and developed first by Ahrens, Kapulkin, and Schulman together, where you define a notion of pre-category first. So the terminology of this varies quite a bit, by the way. So I'll stick with one choice of terminology for now. We say pre-category is something that has a type of object, sets of morphisms between any two objects, and then identities and composition and so on, satisfying the category axioms up to propositional equality. So from now on, I'm working in, at least terminologically and maybe foundationally, in homotopy type theory, univalent foundations kind of setting. So set means what could be called an H set. It means a type where the equality is proposition valued. And so we can see this is very analogous to where E category, except for the sets and the setoids and setoid equalities are replaced by sets and propositional equalities. And then we say that a pre-category is saturated, which can also be known as univalent, or which can also be known as sort of dignifying it with taking its pre off and calling it an actual category, but I'll stick to saturation as the term for today. If, for any objects, the canonical map from equalities between them to isomorphisms in the category is an equivalence. In other words, equality of objects, equality in the type of objects of the category is exactly isomorphism in the category. And of course, classically, no non-trivial pre-category can be saturated because equality is always proposition valued. Isomorphism in a reasonably non-trivial category is not proposition valued. Objects won't have multiple isomorphisms. So posets are the only kind of common classical examples of saturated pre-categories. But in a univalent setting, most natural examples of categories that you come up with are saturated. I mean, so many of the most important ones, including, firstly, the category of sets is directly or the pre-category of sets, sorry, I'll try to stick to that terminology, is saturated by the univalence axiom, gives us that. And then algebraic structures built on it turn out to also be saturated categories. That's the structure identity principle, or one form of it. And many important categories, constructions on categories, preserve saturation. A few constructions break saturation. And when that happens, there's a construction given by Aronskopilk and Shulman, the res completion, which it's a kind of quotienting construction that adds the isomorphisms of the category as equalities in the type of object. So it takes whatever the type of object was, and it sort of replaces its original equalities with the isomorphisms of the category. So you have this quite nice setup with pre-categories, saturated categories, and also there are several other variants on this out there. One that's been used quite a bit was one that Vygotsky was keen on, and so it got formalized in the Unimath library, which was the same thing as before, but dropping the assumption that the Hom types are sets, since there are both examples of interest where that doesn't hold, and a lot of the results one can prove without that assumption. And the reason that I'm bringing this up in relation to what we had before is because when you try to kind of fit these into a slightly more systematic picture of what's going on, you can end up with finding that E categories are the maximally unsaturated notion. That let's change terminology a bit for the sake of talking about things more easily. Take an E category, and for the moment, briefly, we'll call the setoid equalities, the elements of the setoid equality types, we'll call those two cells, which is a hint towards the higher category direction, of course, which we won't pursue today, but it's a fairly unsubtle hint that I'm dropping. And we can say that an E category is two saturated if equality of two cells is always trivially true. Any two cells are equal. So that's saying that each type of equalities between any two arrows is a mere proposition. So that it's one saturated if equality of arrows is precisely two cells. In other words, that's saying that the setoid equality is on Hom setoids is the actual propositional equality on the types of those setoids. And finally, say that it's zero saturated if equality of objects is isomorphism. So the pattern here is that the saturation condition says for each sort in turn that equality on that sort is equivalent to indiscernibility with respect to higher sorts, to saying that things are equal, propositionally equal, exactly if what the higher sorts can see about them is the same for the two things. And this point of view has been developed by Tsemensis, Shulman, Ahrens, and North, and I think some other authors. It's a general idea of saturation in fold dependently sorted structures. And then this kind of hierarchy of notions of saturation on E categories gives us both the Ahrens-Kapulk and Shulman pre-categories as a special case as being the pre-categories are the ones that are saturated in dimension 1 and up. Unimath's pre-categories are ones which are saturated in dimension 1, but not necessarily in dimension 2, since you have Hom types, not setoids. They don't have an extra relation given separate from their propositional equality, but we don't assume that that equality is prop valued. And then finally, for either the Unimath or the AKS approach, the saturated categories are the E categories which are saturated in all dimensions. And so this sees we have a kind of a clear systematic hierarchy of levels of saturation, which firstly organizes it quite nicely, also explains some of the things about which constructions things are closed under. Why, for instance, the unimaths pre-categories, while they're nice for some purposes, they're not closed under so many constructions as other things so unproblematically, that some constructions you need to suddenly pull in this assumption that the Hom sets are really sets. And that can be seen as coming from the fact that their saturation wasn't a sort of such and such an up, but they are satisfied in the middle dimension without being saturated in the higher dimension. That the notions which are saturated in kind of some dimension and all higher dimensions are better behaved under the constructions they're closed under. So was it something? I think there was something else I meant to mention on this slide and I'm forgetting what it was. Right, anyway, yes, right. So we've got this, oh, right, yes, right. And what I wanted to finish up by saying was we've got this hierarchy that kind of organizes the notions of categories with different amounts of saturation and shows that E categories arise very naturally as the maximally unsaturated notion among them. And so we can then port this idea one dimension down back to setoids and say simply a setoid is one saturated if its equality of setoid equalities in it is trivially true, so if its relation is proposition valued, and it's zero saturated if equality of elements is setoid equality in it. So that's if its setoid equality is the actual propositional equality of the underlying type. And so a zero saturated setoid is essentially just a type. It's got no extra data from the relation. And a greater than equal to zero saturated one is precisely a set in the hot sense. And taking the quotient of a setoid is now clearly analogous to taking the rest completion of a category, pre-category, or whatever one wants to call it. Taking the rest completion of any not completely saturated kind of category. And so this gives us a strong analogy that unsaturated setoids and working with them is analogous to working with unsaturated categories in traditional mathematics, which is a completely standard and unavoidable thing in traditional mathematics, because in a non-homotopy foundation, you can't have your non-trivial categories being saturated. And so classical category theory is all based on working with non-saturated categories. And this analogy really, once you sort of look for it and look at it in practice, it goes surprisingly far. That, for instance, the bureaucracy that we complain about in the setoid hell, similarly, in category theory, if you're really, again, you see it unavoidably if you formalize it, but also, and it's there doing traditional pencil and paper maths as well, you always have these ubiquitous functoriality and naturality lemmas, which often are not precisely stated because they're boilerplate. They get so straightforward, so boring to write out every time, but at the same time, you need to have them. I mean, and this was indeed, and especially in the early days of category theory, it was a common kind of complaint, joke, whatever, that a category theorist sort of anything they do, or an algebraic geometry of the Grothendieck school, everything they would do, they would pause afterwards and say, oh, and it's functorial, that you have boilerplate. And so there's a kind of spectrum of responses you can have to this, which on one end of the scale is to say, right, and so for the same reasons that unsaturated categories are bad, that setoids are bad, unsaturated categories are also kind of bad. They're also a hack. We should be always primarily working with setoids, with saturated categories, just like classically when we have a setoid, an equivalence relation, we take the quotient. Similarly, we should take res completion whenever we have an unsaturated category. On the other option, you could say setoids are just as good as traditional categories. We know traditional category theory, it's done absolutely fine. It's been great for organizing large areas of maths. It has this boilerplate bureaucracy, but that doesn't cause a problem. I mean, people just say it's functorial, it's natural. We're all quite used to dealing with that. It's proved perfectly workable and has been accepted as a genuine part of mathematical practice. So maybe we should, this is an argument that setoids are not kind of just hacky thing for better computational content or something, that they really should be more respected as a genuine part of mathematical practice. And I think both these responses have good points to them, have good insights to them, although you can tell slightly by the colors I've used which one comes closer to my heart. But no, I think I don't want to sort of really commit to either one. They both are useful and nice points of view, and they point us. The analogy, I think, helps point up some of the advantages of each thing. That the reasons why we do like classically to take quotients, they're not imaginary. They are good reasons, and those are also then arguments for advantages of using res completion and saturated categories. And similarly, the ways that we've got used to dealing with category theory and the boilerplate it needs and the various other implications of it being in some ways an unsaturated notion are helpful for, I think, reconciling ourselves and maybe classical mathematicians to the idea that we can work with setoids quite happily. And so maybe really the setoid hell, maybe we've all been overestimating a bit, that part of why we see it is because those of us who work with setoids are very often doing it for the sake of formalization. And that setoid hell just happens, it's one of those things which are particularly cumbersome in formalization, which category theoretic boilerplate is as well. Whereas when one's doing traditional pencil and paper mathematics, then both kinds of bureaucracy and boilerplate, they're all straightforward enough that they can be, that they don't create such a high overhead. They can be dealt with happily by just saying, clearly this is extensional, clearly this is functorial, and so on, and leaving it routine to check. And that after one's dealt with the first few pitfalls, one's got the good organizing frameworks of the translation and the e-categories to guide one through a few of the slight subtleties, once one's got those subtleties kind of well ironed out, guided by those good frameworks, then after that, all we've got is this boilerplate, and we know how to deal with that, and we're used to dealing with that in category theory, and in plenty of other things and plenty of other areas of maths. It's not just these places that we have that kind of boilerplate that's needed. So I think that's where I'll want to end, or on one more nice photo of Erik from the same set at the Mittag Leffler. So thank you very much.
Thank you, Peter. Let's thank Peter by a silent applause. All right, very interesting. I've seen some questions in the chat. Maybe some of the people who asked them want to unmute themselves and ask them themselves.
I think Val should go first.
Okay, Val.
Thank you. Thanks, Peter, for a nice talk. That was actually a very light comment, because in your introductory slides, you said that, well, setoids look like weird for traditional mathematicians and alien, but I believe that we are all used from primary school to deal with a setoid of rationals, and we don't even notice that it's a setoid, and everything is so natural there. So anyway, you might wish to reconsider this. That's all I want to say.
Right, I think, right, I'm not arguing that they are alien or unmathematical, but they are often accused of being it, at least. A lot of people react to them, especially coming from classical mathematics, react to them by finding them unnatural.
Maybe because they haven't noticed that I actually know the setoid of rationals.
Yeah, that's what I would. That's also what I would expect.
They
Yeah.
never realized that.
Yeah.
Yes.
Can I ask a question?
I think there's me now. I was wondering if there is a notion of pre-sheaf of setoids, and maybe also a Grothendieck deconstruction that turns a pre-sheaf into a fibration.
Absolutely, yes. Those like, so you can say what a given an E category, a pre-sheaf on it is just a contravariant functor into the E category of setoids, and the Grothendieck construction works absolutely fine and comfortably for that.
So the fibers of the fibration will be setoids as one would expect. Okay, okay, that's okay. Thank you.
Very good. I think Peter is next.
Yes. So I mean, so you talked about the translation from extensional type theory to intentional type theory. So I think, you know, the first person who worked on this was Martin Hoffman, but he had problems translating universes. So maybe the first question is, yeah, you referred to the work of Millie and Giovanni, right? And so I just like to know what is the state of the art of this translation?
Right. So I think there, especially for the subtle issue of universes in setoids, which is one of the big subtleties there. That since we've got Millie here, I don't know if we've got Giovanni here, but we've certainly got Millie here. I won't try to answer that when she's here. I'll ask.
The status of the translation of the universe was precisely studied by Erik before he was dying, and he wrote a paper per print, which I cited in my abstract, and dealing exactly with the universes. He didn't, when they proof checked the translation of his framework in taugh. So you can have a look at this, where I haven't studied it myself fully, but he proposed a solution for it. I don't have a solution for translating the universe. And okay. May I ask a question after?
May I actually extend that answer a bit, since yes, so since you mentioned this this development of Erik's, which effectively gives a version, it formalizes a version of the cumulative hierarchy based in type theory, and uses that to build a setoid universe. And it's, I think, right. And having not thought about this carefully recently, I don't want to definitively say what this, but I think my memory is that it's building on Axel's
yes
version of the cumulative hierarchy, but also refining it a bit in some ways. And yes, so this is a very nice one. And in fact, when I said, no, I guess there wasn't a slide mentioning it, but when I was talking about the conversations that Erik and I had in my first few years at Stockholm, that was when we were each kind of working on developments using it, and it was this development of his that was the one he was mostly working on, that we were discussing this based on. So yes, a lot of the ideas in here are ones that came out of talking about that development in particular.
Yeah, that's a good answer. I mean, I actually read this paper, so maybe I should have realized this myself. But so this is, I think, important work. But it's important to understand that it's a kind of different translation than the one Martin Hoffman tried originally.
Yes, yeah, because Martin Hoffman didn't consider the category, let's say, of bishop setoid, total setoid, which is in the book, and which also Erik took. Martin Hoffman had three different definitions, but of kind of setoids, but no one is the one which corresponds to, let's say, the exact completion of a suitable doctrines based on Martin Lumsdaine theory. So yeah, it's a different, and it validates different rules of type theories, of course. It's in the whole thesis, PhD thesis by Martin Hoffman was one sort of inspiration for us for the minimalist foundation. This is, yes, it is true. So I wonder whether I can...
Sorry, this reminded me of another thing I wanted to add to that answer.
Yeah.
I'll let you get to your question in a moment. Which was that this issue of the fact that it's quite difficult to give universes in the setoid translation. It's effectively that universes of setoids naturally want to be E-categories, not to be setoids themselves. And it's very closely related to the fact that in a univalent setting, it's hard to find or to construct a set universe of sets. And you've got a univalent universe of sets, but not a set universe of sets. And most of the time that doesn't matter and you don't want it. But for some things, it would be very nice to have it. So yes, sorry, yes.
So Peter, may I say something? Just a comment that for me, the setoid construction is a model And what I call as theories for mathematical development are like the usual axiomatic theories, let's say, where you don't work with a model, but you work with the theories. And in fact, the whole business of the two-level foundations is to not work within the setoid model, but to work with the theory which is modeled in the setoid model, and it approximates it. Hopefully, I would like to have a fully complete abstract theories that axiomatized let's say, the setoid model, which resembles the exact completion of a suitable lex category, which, or let's say, weakly lex category. Because the setoid construction can be also described categorically by turning the type theory into a doctrine, suitable over doctrine, and then describe the setoid model as a kind of quotient completion, which is one of the main study I pursued. And one thing that I want to comment, which I liked a lot, your talk, by the way, and this view of turning setoids into categories. And I would like to stress the fact that for me, the construction of setoids is a way to pass from proof irrelevant theory to proof relevant one. So to have these two different, like you do in homotopy theory, you have a mere proposition and you have the actual proposition as a bishop or Martin Löf. And so it's important to study this passage also at a categorical level, to know what properties can be transferred from one to the other and what properties fail. For example, a key point in these two levels, what they call this difference between the theory you start from, the setoid model, is, for example, regarding the axiom of choice. Because you might have, for example, what is the unique choice at the level of, let's say, categories, it translated into the axiom of choice of Martin Löf when you talk in the underlying categories. So it's important for me to study this topic, also to produce models and of extensional theories, and also to study the transfer of properties of the construction from the theory below, let's say the doctrine you start with and the quotient completion you do. I view it as a quotient completion, let's say. I don't know how you view, what is your res completion? What kind of free property does he have?
Right, so the res completion is the free saturated category containing a given pre-category.
Ah, so it's only, okay.
So, right, it's a bit of a different flavor from the exact completions and things. It's much more analogous to taking the quotient of a setoid. It's not a category of quotients, it is itself a quotient of the category, is the feeling to have.
Okay, thank you.
Thank you for this interesting discussion. So we have time for one more question. So I see Steve Vickers has raised his hand.
Just before that, sorry, I just want to say in response to Melise, yes, thank you very much. I very much agree, I think, with most or all of what you say. And then especially the point about the link with proof relevance, proof irrelevance. That's a good kind of keyword that I didn't mention, that this is absolutely very importantly related to the different setoids versus quotienting them, very closely tied to working proof relevantly, proof irrelevantly. So thank you for adding that keyword that I hadn't.
Thank you.
Yeah, well, thank you for the nice talk. And it raised questions in my mind that I hadn't actually thought of before with regard to point-free topologies. So you often find there that, you're quite happy to have quotients of sets, discrete spaces, but when it comes to more general spaces, locales, formal topologies, even toposes, taking quotients becomes really quite problematic. And there are some quite deep techniques involving descent and particular nice kinds of surjections for working with spaces and equivalencies rather than by taking the quotients. So for instance, with the Dedekind reals, there's a space of those, but dealing with them seems a little bit unconstructive. in a computational sense. So you can get a space of coded sequences over it, surjective over it, and you can reason with them and then prove that they give the same result regardless of equivalence class. And that becomes a bit more computational. So that's actually a different foundational setting from the type theory that you're working in. And I wondered if you'd thought of that kind of connection.
No, I haven't thought about how that fits into the setting at all. Yes.
Okay, and I hadn't until you gave the talks. But it's something that's very much on my mind. So, for instance, taking quotients of toposes, that's quite. Taking a quotient of locales can often give you a topos instead. So, and you get some rather deep results coming out of that. Okay, well, thank you for the talk.
Maybe a final comment from me too. I just think it's very nice that we had occasion to bring up Erik's last paper here, because I think actually it's very important, and it's checked in Agda. So we really know that you can interpret the extensional type theory in intensional type theory, although it is in a bit of an indirect way. But I think this is a really important contribution to a question that we have been being puzzled by for decades. So yeah, so I think this is really nice. And maybe I should just mention that Erik said that he thought working on this paper, it was a little bit like knitting, it's something that he kind of did at night. Sort of, took a long time and not very difficult, but of course the main ideas are really important.
And I realize we're over time, and I should absolutely hand over to Christian quickly. But I'll just point out that in this picture one can see a universe on the background in the blackboard. I think it's in the background there. All right. Yes, I'll stop there.
Very good. Thank you, Peter. Let's all clap again.